Thanks, everyone, for being here, and thanks to the organizers for making this conference happen. I'm going to tell you about a topic I've been obsessed with over the last few years. I'll sort of tell you the course of my obsession, and then I'll tell you the latest development. And the topic that is separable states. So we have states that are entangled, and states that are not entangled are called separable. And there are a number of interesting complexity-related problems about separable states, which I'll tell you about first. I'll tell you then about how to approximate them, and then about how the techniques for doing this actually generalize far beyond separable states to operator norms for general spaces, general Banach spaces, as I'll tell you about. This has many, there are many versions of this sort of general theorem, and then I'll close by talking briefly about the simplex. Okay, so by separable states, just let me be very concrete. If you have two parties, then they can be classically correlated but not entangled. And the way we capture this is we say a state is separable if it can be written as a convex combination of product states. So this P is a probability distribution, and these V and W are unit vectors. Another way of saying it is if conv means the convex hull, it's the convex hull of all pure product states, and the pure is unnecessary. It could just be the convex hull of all product states. That's the same thing. Okay, so this is separable. Everything outside of this is entangled. There are a few things we'd like to do with this set. It's one thing we might do is we could ask, well, given a state, let's say I've made it in the lab, or someone else has made it in the lab, let's say, and they've perfectly determined all of the entries of the density matrix. Is their problem done? Can they tell if they have entanglement or not? Well, this is not obvious. This is the weak membership problem. And it says, given a state rho, is it in the set or out of the set? And in fact, that's a little bit too hard because you might be very, very close to the set. So we say weak membership because we say, well, let's say you're promised either be in the set or be some distance away from it. Can you distinguish those two cases? You don't have to exactly nail down the boundary. And this is a convex set, right? This is a convex hull of a bunch of points. And so the weak membership problem is roughly equivalent to the linear optimization problem. This is not true for all sets, but it is generally true for convex sets. If you can do one, you can do the other. And H-sep means the support function of the separable states. So if M is a measurement or an observable, then we might try to maximize trace of M times rho, where rho varies over all the separable states. Okay, so this is basically maximizing a linear function over this convex set. This is mostly the problem I'll talk about for the rest of the talk. It's equivalent roughly to the weak membership problem. It also occurs directly in things like QMA2. If you have quantum Merlin-Arthur games with two unentangled provers, then it boils down to solving computing the support function of the set of separable states. And later I'll talk about some more connections as well. Okay, so how hard is this problem? Let's fix this as size. So you have two parties, each with states of dimension n. If this boiled down to some kind of eigenvalue problem, some kind of small SDP, like checking if the partial transpose is positive, we would hope for something that's polynomial in n. But it's actually much harder. So some of the early results here are to say, suppose you want to estimate the support function, h-sep of m, up to 1 over poly precision. And just to set the scale, I'll say 1 over poly times the operator norm of the matrix M. Well, this is basically NP hard. You can reduce this. There's a reduction from 3 set instances of length n to computing h-sep of matrices of roughly size n by n. So this means that you not only don't have a polytime algorithm, if you believe 3 set takes exponential time, there's really, this is a much, much harder problem. But what about constant error? In most operational tasks, we don't want vanishingly small error, but we want some kind of reasonable error. And here, I'm sorry I changed notation. The subscript op means the operator norm, and then I also use the 2 to 2 norm. Anyway, they both mean the operator norm, the largest singular value. So this is a much coarser approximation, right? Suppose you want to distinguish, let's say the case when, let's say M is a projector, and you're promised that either, so the operator norm is 1, and either h-sep is equal to 1, or it's equal to 0.01, right? So that should be way easier. These things are very far apart, and yet we still don't know how to do it in polynomial time. If you could solve this problem, you could solve a certain version of the planted-clique problem, and you could also solve a 3-set instance of length roughly log squared of n. So if you believe 3-set takes exponential time, this should take time n to the log n, so slightly above polynomial. And so that means, there's heuristics like PPT, but whatever clever heuristic you come up with, if it runs in poly time, it won't work even to this extremely coarse level of approximation. I should mention Stanislaus' talk yesterday, or earlier in the conference, was related to ruling out this sort of approximation of separability testing. Finally, what about a multiplicative error? Suppose that we want to determine this thing up to a multiplicative factor of 100. So this thing is either greater than c or less than c over 100 for some threshold c. 100 is a sort of arbitrary constant here. It turns out if you could solve this, then you could solve small set expansion. Small set expansion is closely related to unique games, which is this problem really at the boundary between P and NP. And I think some people think it's hard, but there's not really a strong consensus about whether it should take exponential time or not. This makes it pretty exciting to be something where we really don't know what the answer should be. And one of the goals of this work has been to try to tackle this unique games question from an unexpected direction. This is all for 2 parties. There's also a multi-party version. And there are a few different works here, but probably the one that's most relevant is by Chen and Drucker, and they said if you have root n parties and you have this approximation in terms of operator norm, again, this is hard as 3-set. And here you have to be a little bit careful because you have root n parties, each of dimension n. So the total dimension of the state is on the order of 2 to the root n. So if you could solve that in polynomial time, that would be 2 to the root n. And this says, well, if you think 3-set takes exponential time, it takes time instead 2 to the n. And so if you scale it down, this comes down to the same, basically it's the same sort of barrier that we don't think you can solve it in time less than dimension to the log dimension, if you kind of scale it appropriately. Okay, so these are all the hardness results. That basically if you want to get very high precision, it's quite hard, but if you want to get modest precision, maybe it can be solved in as little as d to the log d. We can't rule that out. Okay, so what about algorithms? What can we achieve? One of the most successful frameworks is due to Doherty, Perillo, and Spedalieri from over 10 years ago, and the idea is to make use of the monogamy of entanglement. The idea is that if we have a state rho AB, we say that it's k extendable if it could be the marginal of an extension from 1 bob to k bobs, such that if you take Alice in any one of the bobs, you recover the original state. And this forms a hierarchy of approximation. So all states are 1 extendable, 2 extendable shrinks it a little bit, 3 extend a little bit more. Each one gets you closer and closer approximation. And it turns out if you take k to infinity, you get the set of separable states. Actually, their hierarchy has some other things, like it uses PPT and so on, but let me not get into that. So that's great, the higher k is the better, but your effort also goes up exponentially. As you increase the number of bobs, your state space increases exponentially, and so the effort goes like n to the order k. So it's an important question to analyze this to say, well, how does this scale with k? And I became more interested in this problem after my hardness result with Ashley in 2010 that I mentioned before. And there was an amazing breakthrough here by Brandao-Christandl-Yard, which seems to almost match the result of the hardness result of me and Ashley. So here, let me define SEP. Well, SEP NM means M parties. So here we're just talking about 2 parties. And what their theorem said is that for special types of M, you get a very good approximation. And these special M basically correspond to 1 LOCC measurements, meaning measurements you can do with local operations and one-way communication. If you look at this formula, so let me try to use the mouse. Look at this formula. The A sub I is the measurement that Alice does. The B is the measurement that Bob does. And the B's add up to less than the identity. And then after Bob measures and he gets outcome I, then Alice makes a 2-outcome measurement, yes or no, and then decides whether to accept or reject. This ordering is to be compatible with the way I defined K extendable. So if for this type of measurement, this is a restricted class of measurements, but in this case, the approximation error goes like log n, square root of log n over K. So this means that K only needs to be on the order of log n before you get a decent approximation. Remember, the runtime was n to the K. So your runtime now is n to the log n when you get a decent approximation. So this seems pretty exciting. It seems like we've nailed down the runtime at this surprising number of n to the log n, which I would not have guessed when I first looked at the problem. Unfortunately, it doesn't quite work. There's this condition that it's a 1 LOCC measurement, and the hardness result doesn't have that condition. So they match in a quantitative way, but not a qualitative way. It's been quite frustrating. I've been trying to improve it. Many other people have been too, but the gap remains. In the multi-party setting, there's a few different versions of it. Actually, the formula I put down is weaker than what's in those references, but never mind. Let's think about the formula I put down applies to what you might call a multi-party Bell measurement. In other words, there are m parties. They each have they're part of the state. They each measure it locally and transmit their message to a referee, who then decides yes or no based on all of the messages the referee receives. So in this case, we can, again, SDP hierarchies are proven to have certain bounds, and it turns out that one of them essentially matches the hardness result of Chen and Drucker. So when you looked at the result before, where there was a suspicious coincidence, you might think, well, you know, you just defined your norms funny, they really have nothing to do with each other. But the fact that in the multipartite case, they really do match, you know, the assumptions all line up, you know, is to me a sign that these, you know, these might be close to the right algorithm or the right runtimes. So this is all past work. Let me briefly sketch the intuition of these proofs. The idea is that row AB, remember, is K extendable. So that means you can extend it to one where there are K bobs. And if all of the bobs measure, then you get, and Alice measures, you get a joint distribution with outcomes, let's say, A for Alice and B1 through BK for the bobs. And this is because it's 1 LOCC. This allows all of the bobs to simultaneously measure. So that's where the structure of 1 LOCC is crucial. If it were some generic joint measurement, there'd be no way of doing this. And then you have your, you know, the proof is via one of these classic double binds that you look at A and B1, and there's sort of two cases. Either they're uncorrelated, in which case you're done. Remember, you want to approximate a separable state. If it's a product state, that's even better. You know, if A and B1 are uncorrelated, that's like they're not, you know, that's like a product state. That's definitely separable. On the other hand, suppose they're not suppose they are correlated. Suppose they're not like a product state. Well, then you can condition on B1, and that will reduce the amount of mutual information between A and B2. And that's basically how the proof goes. And the log n comes because your progress measure is an entropy. Right? Every time you go, you cut down on the amount of mutual information, and it started off as scaling like log n, so the number of times you have to iterate this should scale like log n. I'm sweeping a huge amount of details under the rug. The proof I'll present to you is actually simpler than than this one right here, but that's sort of the intuition for why it works. So anyway, as I said, there's a suspicious coincidence in these n to the log n's, right? We have this this n to the log n, which appears in this algorithm and the hardness, which really come from two very different places. And I'd very much like to bridge the gap. And of course, some other questions are, can we find these multiplicative approximations that apply to unique games, or otherwise tackle the small set expansion problem? And now, I don't know how to explain the suspicious coincidence. Instead, I will offer you another one. I will give you another algorithm that runs in time n to the log n, which to me appears completely different than the SDP one, and the analysis also seems completely different. And so I'm hoping someone in the room can help me understand what's going on a little bit. The one thing I can say about it is that I will present to you the entire proof of the algorithm. There's just one thing I'll take from another paper, but it's really almost self-contained. Okay, so all right, if you'd fallen asleep, you can wake up again. This is the main result. So if m is a measurement, and I now want it to be a measurement, a 1 LOCC measurement, but where Alice sends a message to Bob. Okay, so we have this sum over AI tensor BI, and the AIs by themselves form a measurement on Alice's system, and the BIs you can think of as just being observables with eigenvalues between -1 and 1. And HSEP, the support function of the separable states, is the maximum over density matrices alpha and beta of trace M times alpha tensor beta. So we can describe this as a process. Alice puts in a state alpha, she gets to optimize over that, and measures it. And then she transmits the outcome of that measurement, which is I, to Bob. And then Bob applies the corresponding B sub I to his state beta, which he gets to choose. Okay, so that's the physical process involved here. And once we write it like that, we see that it can factorize in a particularly natural way. So if you expand out M, you see that this support function is the max over alpha and beta of this sum of something coming from Alice, trace AI alpha, and something coming from Bob, trace BI beta. And now, let's try to break this up a little bit. Let's look at the message that Alice sends to Bob. So I said that if she gets outcome I, she sends, outcome A sub I, she sends message I to Bob. So let's let P denote the probability distribution that she obtains in this way, okay? So PI is just the trace of AI times alpha. It's a probability that she gets outcome I. And we'll call the set of all possible P's, we'll call that S. And then the maximum, instead of maximizing over alpha, we can just maximize over P. Because alpha just shows up once. The only point of alpha, you put it in, and then Alice gets some distribution over measurement outcomes. So once you know the distribution over measurement outcomes, you don't care about the alpha that it came from, right? Just knowing P is enough. And so the picture looks a little bit like this. Alice inputs some density matrix, and let's say the set of density matrices is a ball. And then this, by measurement, gets mapped to the simplex. That's this triangle here is the simplex. Those colors really look very different than on my screen, but hopefully you can see what's going on. The triangle is the simplex, and then that weird shaped thing within it is the set S. Alice cannot achieve all probabilities by her choice of alpha. She can achieve some subset of the simplex, and that's the set S, the ones that are achievable, corresponding to her measurement, the ones that are possible. Then, this in turn translates into some measurement that Bob does. So let's see how this goes mathematically. Let's go back to this expression on the right. And you can see that the maximum over beta, if you carry it out, just gives you the operator norm of what's left, right? Because if you look at this previous line, it's trace of beta times a bunch of stuff, and you're maximizing that over beta. So what's that? That's just the largest eigenvalue of that bunch of stuff that you're maximizing, that you're tracing beta against, okay? So it's just the operator norm of, the rest of the stuff there. And so, let's look at what's the operator norm of. It's the operator norm of the sum over PI times BI. And so you can think of this as you take P, your probability, and then you further map it to a measurement. And this measurement is what I just said, sum of PI, BI. And so that's why you have this, start with the density matrix in a ball, you move to the simplex, which is like the triangle, or rather this purple subset of the simplex, and that in turn gets mapped to the space of measurements, which I'm going to represent as a square. And we could talk about this also as a norm over the set of probabilities. We could say that the B norm of a probability distribution P is this operator norm of sum over PI, BI. Right? That's just a little bit of terminology. And now this is ultimately the thing we want to compute. We want to maximize P over the set of achievable S. We want to maximize this quantity right here. Okay? And this quantity also is easy to compute. Each one sort of by itself is easy, but as we saw, when you put them together, it becomes hard. Now, we'll try to solve the problem by using epsilon nets. An epsilon net means if you have some space, it's a collection of points that's within epsilon of any point in the space. Okay? So I guess what the photographer was trying to do is a packing net. He wanted all of you to stand at least 2 feet away from each other. And that's what you want for an error correcting code. You want every code word to be at least a minimum distance away from each other. I'm talking about a covering net now. I want the opposite. I want to say every point in the space is within, let's say, 2 feet of some point in the net. Okay, so it's sort of complementary to a packing net. So these are covering nets. And this is basically how we do brute force search, right? Suppose I was talking about this fancy SDP method for solving the problem, but you could always try to brute force the problem. Just enumerate over all the possible inputs. And then, okay, well, there's infinitely many possible inputs. And then you say, well, all right, fine. Just do it up to, k bits of precision. And, that's a finite set. Of course, it's really huge. And so we kind of think of epsilon nets as being like brute force, as being like exponential time, naive, not really good idea. And I kind of thought that for a long time, too. And it's not totally wrong. So if you look at an epsilon net for the set of density matrices, then the size is going to be scale exponentially with n. And you could also take an epsilon net for the space of measurements. Of course, you have to do some kind of filtering. You have to say, for every point in the net, is this measurement achievable? But that's a reasonable computation. That net would also have exponential size. But you can see from this diagram, there's another possibility. And that's to take an epsilon net for the simplex. Actually, this is another thing that was in Stanislav's talk. He showed all these different convex sets with their properties, and the simplex was in some ways uniquely nice. Let me not get into that, but basically the size of the net scales like m to the log n over epsilon squared. M is the number of measurement outcomes, n is the dimension, but you see it's all quasi-polynomial. So that's, if you believe that statement, that's almost enough for the algorithm. Let me now show you how the rest of it goes. I claim basically that there exists a small net for the simplex. Okay, this is pretty much the only hard technical step of the proof, and it's not that hard. So how are we going to find a small net for the simplex? We're going to look at sparse probability distributions. So we say a distribution is k sparse if every entry is a multiple of 1 over k. So like 5 sparse, an example would be 3/5, 1/5, 1/5, and then a bunch of zeros. You can think of that also as an empirical distribution over 5 samples. So if I take 5 things and I pick one of them at random, I get a 5 sparse distribution. And that's how we're going to construct them. So the claim is that these k-sparse distributions give you a good net for the simplex. This is not original to us. This idea has been used many, many times in different fields. And our claim specifically is that if you have a point P in the simplex, there's a nearby k-sparse point Q. How nearby? Well, the distance is square root of log n over k. So if you take k to be log n, you get pretty good distance. So that's the claim. And the proof is very short. It's just due to the operator Chernoff bound of Alschwede and Winter. What the operator Chernoff bound says is that if I have some average over a bunch of matrices, and I sample from that distribution, I'm going to quickly converge to the average. Just like the regular Chernoff bound says for numbers, the operator Chernoff bound says for matrices. And how quickly? Well, let's say take k samples, and the matrices all have eigenvalues between -1 and 1. The regular Chernoff bound would say, I'm leaving off some constants on the right-hand side. This is a mild lie, but the regular Chernoff bound would say that basically the probability that you're epsilon off from the average goes down like e to the minus k epsilon squared. It's like the Gaussian approximation. And then the operator Chernoff bound, it can't be quite that good, right? Because suppose they were diagonal matrices. Then every entry of the diagonal would be like an independent, a separate thing. It could be arbitrarily nastily correlated. And so if you want all n entries of the diagonal to independently be close to their average, you'll probably need some kind of union bound, and you'll give up a factor of n, right? So the right-hand side is n times e to the minus k epsilon squared, because it's like the regular Chernoff bound, e to the minus k epsilon squared, but made worse by this factor of n. And then, of course, matrices aren't just diagonal. They can have eigenvectors pointing every which way, but it turns out diagonal is kind of the worst case. So that's the content of the operator Chernoff bound. If you haven't heard of it before, you should probably leave my talk and go read about that, because it's more useful than what I'm talking about. But it's a wonderful theorem. So that's it. So from this bound, you can see if you take k to be, log n over epsilon squared, that probability is going to be less than 1. And you don't need it to be high probability, you just need there to exist, because the algorithm is going to enumerate over all possible k-sparse things. You just need to exist one good choice of sample. And so what does